Hello and welcome to an episode of The Central Equilibrium. I'm Eric Cai, the Chemical Statistician, and I'm pleased to welcome my guest, Christopher Salahub, who will talk about Markov chains. Chris, welcome to The Central Equilibrium.
Oh, good to be here.
So tell us about your educational background.
Well, I just finished actually this last June a 4-year degree, my bachelor's at Waterloo. It's in mathematics, and I focused on statistics.
And what's your occupation now?
Well, I'm currently an intern for the summer here at Environics Analytics, but I'm going off to do my master's at ETH Zurich in the fall in statistics as well.
Excellent. And what will you be focusing at ETH Zurich?
Well, my master's thesis is going to be on using scagnostics and copulas.
Okay.
But beyond that, probably just learning a bunch more and enjoying Europe a little bit.
Okay. All right. So what's your overall objective for today?
I just want to provide a kind of brief overview into Markov chains. They're a really popular model. They're a very powerful model, but I know a lot of people lack some of the more basic ideas of what they are. And so they're kind of limited in how they can apply these beyond using an already generated simulated annealing or Markov chain sampling package. So I want to provide them with a little bit of background to maybe give them that bit of a push to look into it a little bit further themselves.
Excellent. Okay. So shall we start by defining what a Markov chain is?
Sure.
Okay.
I guess the easiest way to start defining it is just to talk about a couple of different things we're going to need to, set up first.
Okay.
So the first thing I want to talk about is imagining just a sequence of variables.
Okay.
We're going to call them xt. X denotes the fact it's capital, so it's a random variable.
Okay.
And t denotes that there's some sort of sequence or time to it.
Okay.
So if we want to write down a series that's like this, so those are supposed to be squiggle brackets.
That's all right.
And we can write t equals 1, 2, ... to whatever number we want to go to.
Mm-hmm.
So we'll call this sequence just x.
Okay.
Now, there's a bunch of different sequences you could make, and a Markov chain is a very particular kind of sequence.
Okay.
It's a sequence which satisfies essentially two basic conditions. I guess 3 if you want to get into the fact that one of them is kind of two independent ones rolled into one.
Okay.
The first of these conditions is that x at t is within some finite set, or at least countable set. So S could actually be infinite as long as it's countable.
Okay. Can you give a quick example of what you mean by that?
Well, an easy example for a finite set would just be, it could be either the number 1, 2, or the number 3.
Okay.
An example of an uncountably infinite set would just be any number from 1 to infinity.
Right.
All integers.
Okay. All right.
So that's the main idea of what a Markov chain is, but the core, mechanic that holds the whole thing together, and this is a mechanic and assumption that essentially not only dictates Markov chains, but also a whole number of other stochastic processes, is called the Markovian assumption.
Okay.
So if we have this sequence and x is a random variable, we can talk about the probability that the random variable has some value.
That's all right. That's all right.
Don't get hung up on the fact this is a little x. It's a general dummy variable.
Okay.
So this is just saying the probability that this value is equal to one of the values from S.
Right. Okay.
We can ask about this probability.
Okay.
More specifically, we can talk about the fact that because this has a time component to it, we can talk about the conditional probability.
Okay.
Of x at t, given x at t minus 1, all the way back to x at 0, which is to say the very first value in the chain.
Okay.
We can talk about this conditional probability.
Right. So this is, you're writing a conditional probability of the random variable at the current time index conditioned on the values of the random variables in all of the previous time indices.
Exactly. So we're essentially saying we want to look at the distribution of the random variable at this time, given that we've watched this process up until this point.
Right.
And we know exactly what its history is.
Right. Okay.
Now, the really convenient thing about the Markov assumption is that it makes this much easier to deal with by essentially killing everything beyond the very last step.
Aha. Okay.
So what ends up happening is this whole large probability ends up just equaling, I guess I'll write it out, in a spot where I have a bit more space.
Later on we can erase the stuff on the top. Don't worry about that.
More or less, the Markov assumption just says that the current state depends only on the last state. I wish I were quicker at writing on a whiteboard.
No worries, no worries. Okay, so hopefully everybody.
I don't know how you can read that, but
hopefully everybody can read that. So what Chris has written here is that P of xt equaling small xt is conditioned on only x of t minus 1 being equal to little x of t minus 1. Okay?
Actually, I'm going to try writing it a different way, and hopefully this will be easier to see. And the second part of this, and this is the part where I say this is kind of...
Try to press against the board a little harder.
Two different assumptions, as it were. So this first part says, I only care about this last state.
Right.
And this second equality says that, and this condition only depends, or this condition is independent of time, which means to say that this probability is not going to change if t is 10 steps in the future, 20 steps in the future. If we know the past state, these probabilities will remain the same.
Right. Right. Okay.
That's essentially what this last step is. So that's two things kind of rolled into one.
Okay.
But if we have this, which is called time homogeneity, it's homogeneous in time, then, and we have this lack of conditioning on anything past the last state, and we have a finite sample space, that's all you need for a Markov chain.
Okay. All right. So let's just recap. So I think you said three things there. The random variable, the sequence of random variables has to belong to some set, and it could be an infinite set.
Countable or finite set.
Okay. So could it be an infinite set, or
it could be a countably infinite set?
It could be a countably infinite set. So as long as it's a countable,
you can
it's fine.
Consider a Markov chain. Yeah.
Okay. And the second condition is that the probability of the random variable in the current state is dependent on only the value of the random variable in the previous state.
Yes.
And then the third is the time homogeneity, which says that the probability of any one random variable, you know what, actually, I don't know how to articulate that third condition. So please
I can articulate that last condition a little bit more clearly. Essentially what it says is, let's consider two states, right? Okay. I'm going to remove this subscript to make it easier. We'll consider two states, x and y.
Sorry, Chris. Let's step back.
Yeah, that's pretty light.
Yeah, it's pretty light, and you know what? We could use a lot more room here. So. No, this is why this will make this a lot easier for you to write here. Okay.
Yeah, I gotta be conscious of the fact that
no worries.
Computer camera is not as sensitive as our eyes.
No worries. Okay, so if you could please just press a little harder on the board and use the thick.
Yeah, that's what I'm trying to do.
There you go.
That's a bit better.
Yeah.
So we just consider two states, x and y. Then the condition essentially says that the probability that x at t equals x given x at t minus 1 equals y is exactly equal to the probability that x at 1 equals x given x at 0 equals y. Which is to say, the probability of going from y to x does not depend on the value of t, which means that no matter how long you run the chain, this probability is a constant. because you could think of some process where the probability of going from one state to another really does depend on the time you're at, how many steps you've gone through the process.
Oh, okay. Okay. So
you could have something where the probability of making this transition decreases or increases in time. But this says that it's a constant. It doesn't matter what time step you're at, this probability will remain the same, which is very important for a lot of the analysis we do.
So are you saying that, let's say if for this probability right here, this is equal to 0.3.
Yeah.
Are you saying that now we're specifically talking about t is equal to 1,
yep,
and t minus 1 equal to 0. Let's say if this is equal to 0.3.
Yeah.
Are you saying that for t at p of x at 57 equals x, p of at 56 equals y, that's also equal to 0.3?
Yeah, exactly.
Oh, okay.
Doesn't matter how far into the process you are, that probability stays constant.
Oh, okay. Okay. Right. Okay. So I think, yes, I think I understand the difference between those last two conditions now. So the second condition says that the probability of the random variable having a particular value is dependent on the previous state, but that conditional probability could change from one time from one time to the next. So the third condition is making even more narrow and saying that probability stays the same no matter what time point we're talking about.
Exactly.
Along this index. Okay.
Essentially, it's saying that the dynamics of the system aren't going to change dramatically in time.
Right.
We have some set mechanics, some set dynamics, set probabilities, and those will be constant as long as we run the chain.
Right. Okay. Okay, thank you. I appreciate that clarification.
Well, it's important because, like I said, those two are typically wrapped into one, which is the time homogeneous Markov assumption, but they really are two independent, assertions, if you will.
Yes, yes. Okay. Good. I'm glad that we clarified that.
But the Markov assumption is actually really important because it allows us to forget, I suppose, a lot of the information about this system that we would otherwise need to worry about. Okay. So if you imagine conditioning on a process that's been running for 50 or 60 steps, then you're doing conditioning on 50 or 60 random variables. Right. And it's going to be very difficult to get anything accurate out of that. Right. This idea of being able to forget most of the past and remember only the last state is a really useful assumption for analysis. Right. Okay. And if you think about it, some people might say, well, this is a very strange assumption to make. Surely history matters much further back. Mm-hmm. The way I think one of my professors always put it was he said that imagine you're applying for a job. Mm-hmm. They're not going to ask you for your elementary school grades or your junior high grades, or many of them won't even ask for your high school grades because you've done university now or you've done some training program now. And so they only really care about the most recent education you've had. They don't care too much about your history beyond that. Right. Okay. I think that's a pretty good analogy to use. Okay. So that's one way of thinking about it, right? Right. Is this the memoryless property that we? It's similar to memorylessness in other variables. Okay. It's more like a limited memory though, right? Because you still do have that past variable influencing the current one, which true memorylessness does not have, right? Okay. Okay. The distribution in a truly memoryless variable ends up being independent of whenever you stop it. In this case, you have some limited memory. Right. Yes. That's right. Okay. So I'm thinking of when I think about the memoryless property. Yeah. So I'm thinking about, for example, an exponential random variable or a geometric random variable. The two of them. Yep. Yeah. So the distribution of any one of those random variables does not change, does not depend on any previous random variable in a process, whatever that came before it. So so that's true memoryless. This is not true memorylessness because it is still dependent on the previous state. Yes. Right. Okay. Good. Okay. I'm glad that we clarified that. So I suppose now that we've talked about it a little bit in abstract, it's a nice idea to talk about what these things actually, typically look like.
Right.
So I'm going to give not really an example so much as I'm going to try and call it an illustration.
Okay.
I'm going to draw a little picture that, I don't know, hopefully communicates a little bit what these things tend to behave like.
Okay.
These diagrams are also useful for analyzing these chains in the future.
Okay.
Right? So let's say we have a Markov chain, and it has 3 states.
Okay.
For simplicity, I'll just call them, 1. I'll just erase my own work with the marker. 2 and 3. That be seen? Yeah, kind of. There's just going to be 3 states.
Okay.
If we want to, we can draw them. Just going to draw them as 3 circles. 1, 2, and 3.
Okay.
Now, a couple of very important properties of Markov chains, I think, are best shown by an illustration like this.
Okay.
So let's talk about these conditional probabilities and how they actually work.
Okay.
In this whole, chain, you can think of the transition probabilities in 9 different ways. There's 9 different probabilities you can think of here, right? I'm going to start writing them out, and hopefully you get the gist of the pattern. So the first one is if you're at 0 at time step 0, if you're 1 at time step 0, you can just stay at 1.
Okay.
Perhaps that's something we want to allow. You could also go to 2. That should be a 1. You could also go to 2, or you could go to 3. And similarly, for all of the other variables, you have the same sort of set, just with this last condition changed to 2 or 3 for the different states.
Okay.
There's essentially 9 possible connections you could have here.
Okay. So, sure, maybe it would be helpful if we go back a little bit. What is the sample space for each of these 3 random variables?
No, these are.
Sorry.
This is the sample space.
Oh, this is the sample. I'm sorry. Okay. Okay. I'm sorry. Wow. That was a. Glad that we clarified that. Okay, so that is the sample space.
That's the sample space.
So a random variable could take on each of these. One of these three values. Okay.
At a time step, it can be one of these values. It could be 1, 2. It could be 3.
Right. Okay. So at one state, it could take on one of these 3 values. In the next state, it could take on one of these 3 values. And so 3 times 3 gives us 9 possible values.
Yeah, exactly.
9 possible different transitions.
Yes, exactly.
Right. Okay. Good.
Now, not all of these need to be actual positive values. Some of them could be 0. You
Right.
could have the case where we say, you know what, if it's at 1, it doesn't go back to 1.
Right. Okay.
It can only go positively or negatively.
Okay. It's okay. It's okay.
How do we trigger that?
The light's gonna come back on. It's okay.
Someone will leave.
Yeah. That's why we have a little bit of light here. Just see. Yeah. I knew it was gonna come back on. Yeah.
Someone will leave. There's people still here.
Yeah.
No, this is the sample space. I suppose I should have made that clear when I was writing it out.
It's okay.
So at any given time step, it can be any of these values.
Right.
And not all of these, once again, need to be positive. They could be any value.
They could be 0 or positive.
0 positive.
Right.
And you have the restriction, of course, that if I took the sum of all of these 3, conditioned on the same initial value, it needs to equal 1.
That's right.
Because you know when you look at it again, it's going to have gone somewhere.
Yes.
It's not going to end. You're not going to look at the chain and it doesn't exist anymore.
Right. So that we're trying to, of course, make sure that we fulfill the Kolmogorov laws of probability.
Yeah.
Right. Okay. Good.
But an easy way to kind of get an idea of what these probabilities are, and rather than having to write out this really cumbersome notation, I'm just going to do this with arrows. So if I draw an arrow from, let's say, 2 to 1, hope that can be seen, I'm going to consider that the conditional probability of going to 1 from 2.
Right.
So essentially, p x1 equals 1, given x0 equals 2.
Yes.
And similarly for any other arrows I draw.
Right. Okay.
And then if I write, I don't know, a number beside that, we'll call it 0.1 in this case.
Okay.
That number is going to be the probability of that transition.
Right. Okay.
And now, of course, there are lots of different ways we can connect these points. That one, of course, being the probability of returning to 3.
Right.
And as long as we satisfy those laws of probability,
yes,
any one of them is equally valid.
Right.
They're a different chain, and they have different behaviors, but any one of them defines a valid Markov chain.
Right. Yes.
Now, if we play around with this for a little while, we're going to recognize there's a couple of different situations that can pop up with any particular point.
Okay.
And these lead to the ideas of communication and classes in a Markov chain.
Okay. Okay.
So let's talk about the idea of communication first of all.
Okay.
Let's focus on just 1 and 2 for the time being.
Okay. Sorry, if we could just quickly interrupt. I realized I said Kolmogorov laws of probability. I think strictly speaking, there are the Kolmogorov axioms of probability. Sorry about that. Okay. Sorry, Chris. Please go ahead.
It's a law by a different name, I suppose. You don't break the law, right?
Yeah.
Let's just look at 1 and 2.
Okay, 1 and 2.
So there's a few different configurations.
Right.
We can imagine that there's no connections between 1 and 2.
Okay. So then that would be 0.
Well, they could still communicate with 3. Yeah, there'd be nothing between 1 and 2, but they still could communicate with 3.
Right.
They could still have arrows between them and 3.
Okay. Okay.
But if you imagine that they don't, let's say that this is the system we have. We have 1, and it only goes back to itself.
Okay.
2 and 3, they happily go back and forth, but there's also a probability that 3 leads to 1.
Okay.
There's no way for me to get from 1 to 2 under this structure.
No, you can't.
You can't go from 1 to 2. You could get from 2 to 1.
Right.
So 2 does go to 1, but there's no communication there.
Right. So what do you mean by communication?
That's a definition. Okay. Essentially, if there is some way that is non-zero to get from one value to another, we say that, that's not communication. What's the technical term for that? There's actually a name for it.
Okay.
I only remember communication, though, because typically the one-directional relationships are much less important.
Okay.
Yeah. If 1 goes to 2, or if 2 goes to 1, but 1 doesn't go to 2, we will say that 1 and 2 don't communicate.
Okay.
However, if instead there's a way for me to get back to 2, even if it's not directly to 2,
okay,
then we say 1 communicates with 2.
Okay. Okay. So communication requires that there is a transition from one to the other, and also in the reverse direction.
Yes.
Right.
It doesn't need to be in one step. It can be in n steps, but as long as there's a positive probability of going back, we say the 2 communicate.
Okay. Okay.
And the important thing about communication is in a Markov chain, communication allows you to actually separate the chain out into different parts.
Okay.
Most importantly, a lot of the stuff we're going to talk about later to do with stationary distributions assumes inherently that all of the states communicate.
Okay. Okay. All right. We'll remember that.
So there's this idea of communication, which is that you can go between 2 states and back.
Okay.
Right? And obviously 2 and 3 communicate because you can just hop back and forth as many times as you want.
Right. Okay. Good.
And by definition, we say that any state can communicate with itself.
Okay.
That's just something we say, even though there may be no positive probability of returning to that state from itself.
Oh, okay. So if the probability of one state going to the same state is 0, we still say that
it communicates with itself.
Oh, okay.
So you could have state 1 over here, and then you could have 2 and 3.
Okay.
So 1 maybe only communicates, or 1 only goes to 2 and 3, but there's no way to get back to 1. So let's say you start the chain at 1. Then at step 2, you're going to be at 2 or 3. You're no longer going to be at 1.
Right. And there's no transition from 3 to 1, so you can't even indirectly go back to itself. Okay.
In this situation, you may in your analysis end up separating these two parts out. So you consider this as two independent Markov chains, as it were. You have this first one, which you leave, and then you have a second one you go to.
Right. Okay.
Right? You may think, okay, there's also some probability I come to 1 and I can communicate with myself. And then you have a question of, well, when do I end up getting to 2 or 3? Like, let's say I start at 1 and there's some probability 1 goes back to itself. What's the probability, or how long does it take until I enter this 2 and 3 relationship? Because I know once I get there, I'm not coming back.
Right. Okay.
When you look at it like this, it allows you to partition Markov chains into these different independent subchains, as it were.
Right. Okay. Okay.
Communication is incredibly important just for getting, I guess, the lay of the land, as it were, to try and figure out how these chains interact and how you can break them apart.
Okay. Okay. Good.
I'm trying to condense stuff a lot here.
No. This is good. I follow what you're saying, and that's the most important thing.
Excellent.
Okay.
I suppose the next natural thing to talk about is something called the transition probability matrix.
Okay. Let's do that.
Let's do that. And the reason why is because although these diagrams are nice, there's not much you can do with this. I can even put I could put numbers on all of these things. I could put a 0.2 here. These both 0.4, 0.4. I don't know. I guess this is going to be 1 and 1 because they don't go any other direction.
Okay.
But this, although it tells you everything about it and you know exactly what all these probabilities are, the chain is fully characterized by this diagram. You can't do too much analysis with this. If I asked you a really tricky question about this chain, you'd probably go at it with a bunch of different probabilities chained together, and it would just be very cumbersome.
Right. Okay.
And an easier way to store all of these values.
Sorry, Chris. Before you move forward, should these two probabilities add up to 1?
No, because
right.
This right.
Okay, right.
Otherwise, yes.
Sorry, thank you. Yeah,
no
right.
Problem.
Right. So one can go to itself, or go to 2 or 3, but these 3 probabilities have to add up to 1. Okay. Right. Good. Sorry, I interrupted you. We're talking about the transition probability matrix.
What makes more sense is the idea of putting these in some organized structure.
Right.
What we would like
And Chris, if you could make sure when you finish writing the matrix, back off a little bit so that everybody can see the matrix on the board.
What we would like is we can write this matrix. We'll just call it, this is the way they always call it, just a big P, kind of vague notation. But what we'd like is some matrix that tells me what all of these probabilities are. And so the way we typically write this notation, and this is purely a choice that has been made, is we write it such that the ij element of this matrix is equal to the probability of going from state I to state j.
Okay.
So for example, in the 1, 1 spot, you have the probability that x1 equals 1, given x0 equals 1.
Okay.
The 1, 2 spot, you have the probability that x1 equals 2, given x0 equals 1.
Okay. So the conditioned state is along the rows.
Yes, this is the conditioned state, and this is the
present state.
Yeah, the present state. You can think of it like that.
Right. Okay.
And so what ends up happening is you end up with this very particular matrix, and this matrix has a couple of rules it's going to have to follow, obviously.
Yes.
The first is that the sum across all of the rows has to be 1.
Right.
Simply because these are all defined probability spaces, so they're just going to have to equal 1 at the end.
Yes.
And that's the biggest constraint. There's a few others, and there's some very good properties about this, but I guess let's just write out this example we've seen here. Once you get used to looking at these things, it's way better than looking at this. You get a much better feel for the system. Right.
I'm just going to pull this a little bit this way just so that
there's
more room. Yeah. Okay. Go ahead.
So we'll write out this matrix or this system we've drawn here a little bit.
Right.
So we have the probability of going to 1 from 1 is going to be 0.2, to 2 from 1 it's going to be 0.4. That's this one right here. And then to 3 from 1, we don't even need to look at the diagram because we know it has to sum to 1, so we know it's 0.4.
Right.
Then from 2, we can't go back to 1, so there's a 0 there. From 2, we can't stay at 2, so there's a 0 there. But we can go to 3, so we have a 1.
Right.
Similarly, from 3, we can't go to 1, so we get a 0. We can go to 2, and we're going to always go to 2. And we can't stay at 3, so there's another 0.
Right. And of course, they all add up to 1 along the rows.
Yeah.
Okay.
And this matrix, I guess, humble as it is, defines pretty much all of the mechanics, all of the dynamics. Everything you need to know about a Markov chain is encapsulated by this one small matrix.
Right.
I mean, it's small here, but you can imagine if you had 10, 15, 20, as many states as you want, this thing gets quite large.
Yes.
And in the case of a countably infinite set, you have an infinitely dimensioned matrix.
Right. Right.
Which is not super good to look at, but you can still mathematically address in a lot of different ways.
Right. And I think implicitly there's another property inherent in this is that it has to be a square matrix.
Yes.
Right?
Yeah.
Okay.
You can't really. It doesn't make much sense to think of a transition matrix that isn't n by n, right?
Right. But to take that one more step, you could start. I don't know if this makes sense. This has a meaning of probability or Markov chains, but does if you have a square matrix, you can start thinking about invertibility. Do inverses have any meaning in probability or for probability transition probability matrix?
Typically, we don't think about these things running in reverse.
Okay.
So even though I suppose the inverse, actually, I'm not even sure it would give you the backwards transition probability matrix.
No, I'm just thinking about stuff.
I totally get it. Inverses are cool. Inverses can do some cool stuff.
Yes, yeah.
No, the more important feature of this thing that we tend to end up looking at is actually the eigenvectors and eigenvalues.
Right. Okay.
Because those end up being more important for the dynamics. So we don't typically think about the inverse of this thing.
Okay.
I'm actually not sure. There could be something significant about it, but in all of the courses I've taken, everything I've read, everything I've looked at, the inverse is never a point of interest.
That's okay. All right. Okay.
So now there's a couple of things about this that we can talk about, and a couple of things about the chain we can talk about.
Okay.
I'm going to be a little bit, I guess, condensed and brief in my, in the way I bring forward these ideas. If you really wanted to look up any of this stuff, it makes much more sense to actually take the time to go through it properly. Because even though I'm going to tell you a bunch of things and tell you what it all means, the fundamental definitions give you way more flexibility when addressing problems. There's a couple of times in a number of courses I've taken where dealing with this matrix is actually a lot less useful than dealing with the more fundamental way of expressing some of these concepts.
Okay, let's dig into them and see what we're dealing with here.
So,
can I erase anything for you?
I'm just going to erase all this, actually.
Okay.
We're going to forget about that chain, and we're going to focus on this transition probability matrix for a little bit.
Okay. Feel free to use the entirety of the board.
I feel like I'm going to catch my chair on the leg of it. There it is. Yeah, I just did. It's too small for me to actually stand up and do it because I'd be stooped over the whole time. But if we have some transition probability matrix.
Did we clean that board too well?
I don't know. It might still have some of the liquid on it. It's all good. We'll just see if I can actually. There we go. Just need to dry off. So if you consider this matrix, I'm just going to use the brief notation for it. So I'm going to use this Pij to represent the transition probability from state I to state j.
Okay. Yeah.
Which makes sense.
Yeah.
And then we're going to have, I is within S, and J is within S. So I'm just using this as notation for a matrix that is n by n. You have all the values in S and I, you have all the values of S and J.
Yes.
This defines, in short, what the transition probability matrix is.
Right.
We're going to talk about something called ergodicity.
Okay.
Ergodicity. I'm going to write it out because it's a strange word. I actually don't know what the origin of it is. I should have looked that up. No, that's ergodic, not ergodic. Ideally, we hope that this is an ergodic Markov chain.
And what is an ergodic Markov chain?
3 things.
Okay.
It is positive recurrent. That's not how you spell positive. It's positive recurrent. It is irreducible. Now this one we actually can talk about a bit more easily because I've already introduced the idea of communication. And what's the last one? Positive recurrent, irreducible, and aperiodic.
Aperiodic. I write out all of recurrent just for everybody at home to see.
For everyone at home.
Okay. All right.
So those are the 3 conditions, and I'm
Okay.
going to talk briefly about what all of them mean.
Okay.
They all have very rigid definitions,
Okay.
and in particular, this recurrence one is a tricky definition.
Okay.
But I'll talk about what they mean in general terms so that we can get on to, I guess, the more interesting meat of what I want to kind of address.
Okay.
Positive recurrence. The idea of positive recurrence is that a Markov chain has a positive probability of returning to a state once it leaves it.
Okay.
So it essentially means, wow, okay, I once again erased it when I was trying to think of it. It essentially means that for some n, the probability is positive returning. And that's specifically the recurrent part.
Okay.
The positive recurrent part modifies that slightly.
Okay.
You can actually think of countably infinite Markov chains where there's a positive probability of returning to a state, but the expected time between state visits of that state is infinite.
Okay. Okay. All
What
right.
that means is you expect to, at some point, return to whatever state you leave, but you expect to wait forever to do so.
Okay.
And that's negative recurrence, which is to say it recurs, but it's a really bad recurrence.
Okay. Okay. So a positive, positive recurrent means that you can go back to the same state, and that the time that it takes to go back to that same state is finite.
Yes.
Okay.
You expect to do so in a finite number of steps.
Okay. Right.
Steps.
Okay.
Irreducible actually goes back to this idea of communication. The idea of irreducible is that this concept of communication actually partitions the state space.
Okay.
So you can break S apart into communicating classes, is what they're called.
Okay.
Which is essentially is sets or subsets of all groups of states which communicate with each other.
Okay.
And the idea of an irreducible Markov chain is one where the entire state space communicates with itself. So every single state within that Markov chain can communicate with every other state in that Markov chain.
Okay. So everybody can communicate with everybody else.
Exactly. You can get from one spot to any other spot in the Markov chain if you give it enough time.
Right. It doesn't have to be a direct communication.
Absolutely not.
Right. So you may need to go through several other states before you can get to your final destination, but there is a path to get there.
Exactly. That's the point.
Okay.
And the final one is aperiodic.
Okay.
So if you remember earlier, I drew a Markov chain. This is, I guess, the simplest one. I called it 2 and 3 then, but I'm going to call it 1 and 2 now. And it had this structure.
Right. Okay.
The idea is of aperiodicity is if you look at all of the number of steps n, such that there's a positive probability of returning to that state, if the greatest common divisor of all of those has the same, or if there's a greatest common divisor that is not 1, you say it is a periodic Markov chain. So in this case, if you consider every time you visit 1, if you start at 1, you will visit 1 on the first step, and then the third step, and then the fifth step, and then the seventh step, etc., etc., etc.
Right.
Which means that if you look at, this is, I guess, step 0, and then step 2, and then step 4, the greatest common divisor ends up being 2. It always is going to go to 2, and then to 1, and then to 2, and then to 1.
Okay.
It forms this cycle.
Okay.
It has a regular period to it.
Okay.
We don't want that in ergodic chain.
Okay. Okay.
The reason why, actually, if you want to think of a simple example.
Yes, please.
I'll get into this in a minute, but this ergodicity is necessary for something called a stationary distribution.
Okay. Actually, before we get into stationary distributions, let's show an example of an aperiodic chain.
Sure.
Feel free to use this one.
Sure.
I have a feeling that black one might be
tapped.
Yeah.
A simple way to have an aperiodic chain, and this will always be the case, is if any state communicates with itself, the chain is aperiodic. The reason why being is because I can get to 2 in 1 step if I start at 1, or I can stay at 1 and then get there in 2 steps, or I can stay at 1 twice and then 3 steps, which means if I try to consider any sort of periodic behavior to this period is going to get ruined by this loop where it can stay at 1 for 1 step. Whereas before it was always switching from 1 to 2 to 1 to 2. This means that I might look at it and it might stay at 1. And that ruins the regular period of it.
Right. Okay.
So if you have a periodic Markov chain, the way it's going to look is, in the case of 2 states, it's going to be, if I just draw this, like we're going to say this is like x0, x1, ... like that, then you're going to have something that looks like 1, and then it's going to be 2, and then it's going to be 1, and it's going to be 2, so on and so forth. There's some regular pattern to the states.
Right. Okay.
But if you have the ability to go back to a state when you leave that state, then there's no regular pattern, because at some point there's going to be 2 1s, and you don't know when that is.
Right. Right. And it could be 1 2 1 1 2 1 2 1 2 1 1 1 1 1.
Yes,
2.
exactly. Or it could stay at 1 for forever. I mean, it's not likely, but it could happen.
Right. Okay. So there's no rhyme or reason. There's no pattern. There's no periodicity to the way 1 and 2 transition between each other.
Exactly.
Right. So that's aperiodic.
That's aperiodic. Yeah.
Right. Okay.
And the reason why we don't want that is because if I asked you, okay, it does this. If I look into, the infinite future, what state is it going to settle at? What is its tendency going to be? There's no good answer.
Right.
Because it's always cycling back and forth, or it's going to be at some defined state at a defined time point. But, asking what what infinity is divided by 2 doesn't make any sense. So we don't know if it's going to be at 1 or 2. We know it's specifically going to be at one of those.
Right.
Whereas if we break the pattern, I can say, as we go to infinity, like what states does it tend towards? And because it appears more random, because it is at that point truly stochastic in some sense, you can actually talk about that sort of thing.
Okay. And I'm guessing that stationary distributions have some nice properties that are desirable for some other
They
applications.
are the core way we apply Markov chains.
Right. Okay.
They're the reason why we go through most of this trouble, I guess, I suppose. And they're the real reason, or the real power of Markov chains.
Okay. Okay.
So if a Markov chain is ergodic, then it has a stationary distribution.
Okay.
Luckily, there's a couple of easy ways to check most of these. Like I said, for the aperiodic one, the easiest check is if any state can communicate with itself.
Okay.
So any Markov chain which has a state that can go from itself to itself, such that, I guess I'll write it out more explicitly. Any Markov chain where PII is greater than 0,
Uh-huh.
for some I, it doesn't matter which I it is,
Uh-huh.
that will always be an aperiodic Markov chain.
Okay.
That's the easiest way to check.
Okay.
Sometimes it's more complicated than that,
Uh-huh.
but this is the, by far, easiest possible condition. And it's usually the case that there is some state that has this property.
Now, this is a sufficient condition for aperiodicity, but it's not a necessary. Is it a necessary condition?
It's not necessary.
It's not necessary. Okay.
You can have chains where you don't have any positive diagonals, but it's still aperiodic because of structures that pop up in other spots.
Right. And by the way, if anybody wondered what he meant by positive diagonals, if you write these probabilities out in a transition probability matrix, then the diagonal entries will be the ones where I is equal to I, right? So PII will be the diagonal probabilities in that transition probability matrix.
So essentially what you do is you look at whether or not there's any positive diagonal element to check this one.
In the transition probability matrix. Okay.
Irreducible, you just do a quick communication check. You start at a point and you say, okay, can I get to any other point and back from this point? And if you can get to any other point and back, well, then you know that you could get from any of the original points you were at back to them, because you just take the path you took to get to that state, and then you go back to 1 and you go back to that state again.
Right.
So you know that there's some path between every state at that point. Once you start at one state and you say, can I get to every state and back?
Right. Okay. Yes, I think I understand what you mean. So if you have, I think what you're trying to say is,
you want to use this?
Yeah. I think what you're trying to say is, so let's say if I have a way of going from 1 to 2 and then from 2 to 3. So let's say if I have a way, and by the way, so I think what you're trying to say is if I could pick any one state, say 1, and I can get to 3, then it means that this whole system is irreducible because
you need to be able to get back to 1.
I need to be able to get back to 1.
If you can get to 3 and back to 1, then the whole thing communicates.
Because it means that I have a way of going from 2 back to 2, because it's just an extra step.
Exactly.
To go from 1 to 2.
Exactly. Right. So if you've gone from 1 to 2 and then all the way back to 1, you know that taking one extra step takes you back to 2, and therefore you've gone from 2 back to 2.
Right.
And therefore you know that every single state communicates with every other state.
Right. You've mapped out the path
essentially
to get back to the original state. So it's just shifting your
loop
by 1. Yes. Thank you. Okay.
Yeah. So that's the easiest way to check for your reducibilities. You just start at one state. You say, can I visit every state and get back to where I started?
Okay.
Can you get back home?
Is there some property in the transition probability matrix that can help us to look for irreducibility?
Not really.
No. Okay.
I mean, obviously, if every single element is filled, then yes. Okay. You're guaranteed, because you can consider the fact that you can go from any state to any other state directly.
Right.
But if you don't have that case, usually it's not. And oftentimes, after you've looked at a couple of these transition probability matrices, your brain is much quicker at recognizing what is and isn't irreducible Markov chain.
Right.
When you first start out, it's not always that clear.
Okay. So if a transition probability matrix is non-zero in every entry,
then
it is definitely irreducible.
Yeah.
But that is a very strong condition. and it seems like what you're saying to me is many of the more interesting cases are ones where there are 0 entries, but it's still irreducible.
Yeah, exactly.
It's not immediately obvious.
It's not immediately obvious.
Right.
I mean, obviously, as well, if you can move, if it's a chain sort of structure. So if you can have, let's say, there's 10 possible states, and you can go from 1 to 2, and you can go from 2 to 1 or to 3, and then from 3 to 2 or to 4, then that's pretty easy to see. You could draw a chain all the way up to 10 and then back down to 1, right? Pretty much directly like this one, right? So from 2, you can go to 1 or to 3, and it's pretty easy to see based off of this that there's an easy sort of chain you could follow.
Yeah, I think what you were trying to say there was if you can go from 1 to 2, then you can treat this as kind of like one.
You can treat that as one
state, and then if you can show that this state can
you can
go to 3,
absolutely,
then that's irreducible because like this is another state right here.
Yes.
Right. And so if you can go from this state to this state, then you've shown that it's irreducible.
Exactly.
Right.
This state to this state and back. Right. You need always go back. That's the idea.
Right. Okay.
And that's actually a nice thing you can do with Markov chains. If you have a bunch that communicate but not with each other, you can split it apart into separate chains.
Right.
Or consider all of them one state. Because, like I said earlier, the technical term, it introduces a partition where they're all equivalent. It's an equivalent partition of the space.
Right. Okay.
So that's all you need to check for irreducibility. Positive recurrence is actually, in general, very hard to check for.
Okay.
There's a couple of conditions you can use.
Okay.
But there are 2 that are very nice.
Okay.
So if you have a finite Markov chain, which is irreducible, it's guaranteed to be positive recurrent.
Okay. A finite Markov chain that it is also irreducible.
So that's to say, if the sample space S or the state space S is finite, and you know that there's one communicating class, it's guaranteed to be positive recurrent.
Okay. And when it comes to common applications in Markov chains, are most sample spaces or state spaces, are they finite?
Yes.
They are finite.
They're usually finite, even though they are frequently very large.
Okay. That's fine. Okay.
And so as a result, this one, in most cases that you're going to deal with, is actually relatively straightforward to check.
Okay.
That sort of positive recurrence idea.
Okay. Cool.
Otherwise, there are a bunch of mathematical definitions. I'm not going to go into them here, but I encourage anyone watching, if you're more curious about it, if you just search up the term positive recurrent Markov chain, you'll find a bunch of definitions, and there's a couple of cool techniques, actually, in conditional probability that you can use to get interesting results with Markov chains and that property.
Okay.
But if it has all of these, then it has a stationary distribution. And what do I mean when I say a stationary distribution? Do you mind if I...
Yeah, please, go ahead. Can I erase anything for you?
I was just going to erase all of this, because I feel like the people at home have had enough time to
please
see those values. It's not like I just flashed it on the screen quickly. What does it mean to have a stationary distribution? The stationary distribution, and actually in the case where you have a finite Markov chain, it's also called the limiting distribution. But the stationary distribution is essentially just, I'm actually going to erase this too, it's essentially just the eigenvector with the value of 1 of the Markov chain. If we call pi the stationary distribution, then the stationary distribution is just the distribution that satisfies pi p equals pi. And pi in this case is a row vector. If there's n states, that's the idea of a stationary distribution. It essentially says if you have a vector that specifies a distribution of points. So this gives you the defined probability that x at t equals to 1. This is the probability that x at t equals to 2. Then the stationary distribution is a distribution where the dynamics of the Markov chain don't change the way the points are distributed if they were randomly sampled. So the Markov chain is at any point. Like xt is always equal to some value, not a distribution, right? If you look at it at a time point, it is equal to some value. But given your starting conditions, given x naught, in general, you don't know what value that's going to be. And if I said, I know that x naught is equal to, say, 5, there is some distribution, if I step forward t time steps, of what this looks like.
Yes.
We can generalize this to say that at time 0, there could be some distribution on x0. So it could be one of any in the state space with some probability. And then we can give it this value of a distribution and consider whether or not it's stationary. I could say there's 3 or there's 2 initial states. The way I pick x0 is I flip a coin, and then from there I have some transition probability matrix. That would mean that the distribution of x0 is 0.5 for value 1 and 0.5 for value 2.
Okay. I think, I'm still struggling to understand. Yeah. Okay, is there a more trivial example that you can actually write out?
Yeah, well, I can write out a trivial example of, like I said, flipping a coin. So the idea is that at any time point, we can consider the distribution of states. I don't know if that cleaner is actually going to help it much right now. At any time step, we can consider the distribution of states, which is to say that that is kind of comical. I don't think this is the markers. I think it's the board.
Yeah.
I don't know. Is it still wet or something? No. There we go.
Yeah. If you use the,
I'm using the thick part.
Yeah. Okay.
Yeah. Anyways, we can consider x naught. Like x naught is definitely equal to some value if we look. But we can also consider starting the chain off with some distribution.
Okay.
So because x naught is a random variable, we can say that, like I said, you have a trivial case. Let's say there's a Markov chain. Its transition probability matrix is equal to, there's going to be 2 states, is equal to, I don't know. We'll just make it very simple. We'll make it 1/2 everywhere.
Okay.
And then we can say, okay, once we have what x is, like if x is, or x0 equals 1, we know what to do. We can say, okay, then there's a 1/2 probability it stays at 1, a 1/2 probability it goes to 2. And if we said, I want to simulate this Markov chain, we could. But the question is, how do you choose this starting point? Okay. And so there could be some distribution on the starting point. I could say, flip a coin to pick whether or not it's 1 or 2. So if it's heads, it starts at 1. If it's tails, it starts at 2. Okay. If I do that, then we can consider, instead of just x naught, we can consider some distribution at time step 0. We can consider, I'm just going to call it d, and it's of course a vector of probabilities at time step 0. Okay. And in our case, the simple example I've given, it is also just 1/2. 1/2. Okay. So the idea of a stationary distribution is, the nice thing about this distribution is if I take this distribution, actually probably should make that clear, it's a vector as well. If I take that distribution and I want to consider what that looks like as time goes on, I'm not going to go through all the proof of it, but it turns out that if I want d at 1, that's simply equal to d0 matrix multiplied with p. Okay. Which is not that crazy to believe if you think about it, because if you think about this, you have a 1/2 probability of starting at 1, right? So you may say at time step 1, what is the probability I stay at 1? Well, that's the probability that you start at 1 and you stay at 1, or the probability you start at 2 and you go to 1, which is exactly what happens if I take the matrix multiplication of this row vector with this matrix.
Right. So you're trying to figure out the distribution of the states at time equals 1.
Yes.
That's your goal, and you can figure that out by doing this matrix multiplication where you have this row vector, which is the distribution of the states at time equals 0, and the transition probability.
Yes.
And if you do this matrix multiplication, then you'll get the distribution of the states at time equals 1.
Yeah.
Okay. And to take that one step further, I think what you're trying to say is, if you can find some row vector, pi, such that pi times p is pi, then pi is a stationary distribution.
Yes, because it doesn't change if you apply the Markov chain over time.
Right.
Which means the distribution of states is going to be the same no matter how many time steps you go into the future.
Right. Okay.
That's the essential idea. Yeah, I should have
Okay.
explained that distribution better. I realized as we were going through, I was like, I didn't.
That's okay. Hey, that's my job.
I didn't plan for that part well enough.
That's okay. That's my job. See, that my job is to struggle through this whole conversation until it makes sense, at least to me, anyway. All right. Okay. Cool. So stationary distributions. I think we understand what that means now.
Yeah. So the idea is that, and more, I guess, in another sense, you can think about the fact that you can generalize this idea of one step to get the distribution forward to have the idea that if you want to consider the distribution at time step n, you're just going to multiply by p n times. So this is shortcuts for d naught, and then you're going to have p, and then you're going to have another p, and then you're going to have another p, n times.
Right, where here there are n instances of p.
Yeah.
Okay.
You can consider the way this thing is going to behave over time.
Right.
And for an ergodic Markov chain,
Mm-hmm.
the stationary distribution is also the limiting distribution.
Okay.
Which means that if you apply this p over and over and over again to any starting distribution, you arrive at the stationary distribution eventually.
Okay. So after multiplying the initial distribution of states by the transition probability matrix many times, some n times where n is big enough, you'll get to the limiting distribution.
Well, it's technically you need to multiply an infinite number of times, but there's a point where you can't approximate.
Oh, right. It's the limit, right?
It's a limit.
If we're going to say the limit, then we have to multiply infinitely many times. Okay, but if we do that, then we'll get a stationary distribution.
Exactly. So the idea of an ergodic Markov chain is that the stationary distribution and the limiting distribution are the same. They exist and they're unique, which means that there isn't more than one. It's going to always tend towards one distribution.
Oh, okay. So an ergodic Markov chain has one and only one stationary distribution.
Yes, and that's the limiting distribution.
And that is the limiting distribution. That's
and
right. Okay.
This, like I said, ends up being equivalent to looking for an eigenvector with eigenvalue.
Right. Okay.
1.
So that sounds like a theorem.
This
whole idea that a Markov chain has one and only one stationary distribution. That sounds like
it's ergodic. Yes.
Right. And what is the name of that theorem so that anybody at home?
I'm not sure I remember it actually.
Okay, that's all right. Okay.
I think when it was presented to me, it was something called. It wasn't called by a name.
Okay.
Like, when I was taught it, I was not given a name of a person who discovered it. I was just told this is the fundamental ergodic theorem of Markov chains.
It's okay. That's okay. Google is smart enough that if we actually, I'm sure that if you search that whole phrase that I just said, an ergodic Markov chain has one and only one stationary distribution. I'm sure that if you search that whole phrase on Google, you'll probably find that proof. But it sounds so remarkable. It sounds so powerful that
it is very.
You'd think somebody was egotistical enough to attach their own name to it.
No, I guess the guys.
I'm being too cynical. All right.
The guys who are doing this were a bit more humble, I suppose.
Right. Okay.
And the reason why that's important, the reason why we want something that will eventually tend towards some distribution, is actually the core idea of what Markov chains are typically used for in everyday applications.
Okay.
So the two main places, or I think one of the main places they're used, I don't know if this is always the case or always going to be the case, but Markov chain Monte Carlo is a very common technique, and simulated annealing and other stochastic optimization techniques are also incredibly common. And most of these rely on the idea of something called the stationary distribution of the Markov chain, and they rely on it being the limiting distribution of the Markov chain.
Okay.
Essentially, the idea is, at the end, I think I'm going to go through an example of analyzing one possible Markov chain if you want to kind of solidify all the stuff I've been talking about.
Yes, please.
But I'm going to quickly talk about the implications of this idea of a limiting stationary distribution. What's up with this whiteboard?
I think if you clean it with a brush, I think it's slower, but it's not gonna destroy your writing in the next instant because you won't have the chemical
alcohol or whatever.
Yeah. I'm a chemist. I should know what chemical is in this wipe. All right, please go ahead.
Essentially, the idea is the way this ends up working. Typically, you can think of a distribution of points. You say, let's say I have some arbitrary distribution. We'll call it. I don't know if it's gonna make a difference. I don't know if it's just the white. Maybe it's me. Sure. We can consider some distribution that we would like to get some sample of.
Okay. Sorry about that. Could you come back?
No, I just got 4 chairs.
Okay, please. Okay, come in.
You guys.
We'll actually give you better chairs.
Oh,
okay.
Nice. Can I give me like 4 chairs?
Take those ones and.
Oh yeah, sure.
Yeah. That's what it's fun. Swap chairs for you guys.
That chair out?
Yeah.
No, that's really stuff. I didn't realize that. It is stuff.
Yeah. Sorry. And that chair you need as well?
Yeah.
Okay.
I'll just give you 2 more. Thank you.
Okay.
Thanks. Thank you very much.
Thank you.
problem.
Thank you. Okay. Sorry for that brief interruption there. Go ahead. Okay. You were saying.
Essentially, if we want to sample from an arbitrary distribution, if we can think of a Markov chain which has a limiting distribution that is equal to the stationary distribution. If we can think of some Markov chain where I'm going to use f as shorthand for this distribution, is equal to p to, I'm going to abuse notation and just put p to the infinity.
Okay, that's fine.
This is just my way of saying, the limiting distribution of this Markov chain.
Okay.
And technically speaking, there is still some d naught there.
Yes.
But because it doesn't matter what that is,
okay.
Typically, when you talk about the limiting distribution, you end up dropping that anyways. So the mathematically typical way of writing that is, of course, using limit notation. That's the way that you're technically supposed to write it down. So I was abusing notation a little bit.
Okay.
But if you can think of a Markov chain that has that stationary distribution, if you run it for long enough, you will start sampling from this distribution regardless of what it is.
Okay.
And moreover, because it's really easy within a Markov chain to move from one step to the next, you're not going to end up with problems of rejection that you would have in the acceptance rejection algorithm. You're not going to end up with problems of having to think of how to create a candidate distribution or how to, propose new points, because it's all encapsulated by this Markov chain.
Okay. So are you saying that if you have an ergodic Markov chain, then it doesn't matter what the initial distribution is? If you multiply by the transition probability matrix enough times, you will get to the stationary distribution?
Yes.
Oh,
and that's why if you've ever heard the term burning time with a lot of simulations, this is usually what they're referring to. The idea that they try to approximate f really closely, right? So they try to create some, we're going to call it alpha naught, that is, pretty close to f, where f is the distribution they want. They want some alpha naught that's kind of close to f. I mean, I guess to be more clear, I should make these vectors, right? Because they're vectors of probabilities.
Right.
You want something that's close to f, but it's not quite f.
Right.
And so when you run this chain that has f as the stationary distribution, what ends up happening is you eventually will choose, or you'll eventually get to f. But the first couple of steps aren't going to be sampled from f.
Right.
Because you need to give it enough time to get sufficiently close to this distribution.
Right. Okay. So it sounds like then that even though it doesn't matter what distribution you start with, it would still be nice to start with a distribution that's close enough to the stationary distribution so that computationally you will reduce the burning time.
Exactly, right?
Right. Okay.
So you could think of some distribution, like to think of a kind of contrived example. Let's say there's some transition probability matrix. such that I'll do that P one more time. There we go. Such that this is equal to, I'm going to say it's a vector, and there's going to be a whole bunch of zeros, and then it's going to be 1/2 and 1/2 in the last two states. Moreover, let's assume that, this is the state. Well, no, this is the stationary distribution, and let's assume we want to sample from this, and for some reason we don't just pick the last two and flip a coin. What ends up happening is, let's say you started with an initial distribution that was equal to something like 1. Oh, sorry, I got confused for a second there. I don't know if the computer can see that, but I'll move over. If I choose an initial distribution like this, it's really not very close to the stationary distribution.
Right.
It looks very different if you wanted to consider the relative probabilities and the way it works.
Yes, yeah.
And if you start here, it's going to take a longer burn-in time to get to the stationary distribution.
Right. Sorry, I think that is just a little bit too small, so I'm just going to rewrite that just so that it's a little bit more clear. So we're talking about, no, can I get that pen, please? Sorry. So it's the limit as n goes to infinity of p to the n is equal to, was it 0, 0, 0, 1/2?
Yeah.
0, 0, 0, 1/2. 1/2. Okay, so that's the stationary distribution that we want. And if we start with this initial distribution, it's not very close to the stationary distribution.
It's quite far, right?
It's quite far.
You can imagine having something where you had 1/3 and 2/3, and you're much closer to that stationary distribution.
Right.
The closer you approximate to begin with, the less your burn-in time is.
Right. Okay.
But the comforting thing is it doesn't matter what you start with, because you will eventually get there.
Right. It might matter if you have a deadline tomorrow and you want to make sure that you get to
I
the
was going to
station.
say, it doesn't matter in a Troy case like this, but if
Yes.
you have a large Markov chain,
Uh-huh.
yeah, the burn-in time can be pretty significant.
Right.
Quite significant, in fact, right?
Right. So in most applications, do you know what the stationary distribution is going to be?
Not always, no.
No, not always. Okay.
So you can imagine a couple of cases. For example, simulated annealing, which is
Uh-huh.
something I'm very confident, very comfortable with.
Uh-huh.
You can create a simulated annealing protocol,
Uh-huh.
which has some transition probability matrix to it.
Uh-huh.
However, if you don't consider the stationary distribution correctly, you may end up with problems. So
Okay.
the Metropolis-Hastings algorithm, if you follow it to the letter, you guarantee that your stationary distribution
Uh-huh.
matches exactly the distribution you want to sample from.
Okay.
And that's because of something called detailed balance, which
Okay.
is a similar sort of way of proving a distribution is stationary
Okay.
to that pi p is equal to pi that I showed earlier.
Okay.
Detailed balance essentially says if I start at state I, the probability of starting at state I and going from I to j
Uh-huh.
is the same as the probability of starting from state j and going from j to I. It's this kind of symmetry problem.
Okay.
And if you have that level of symmetry, then you have a stationary distribution.
Okay.
Um,
I wonder, did I ask a really trivial or stupid question? Because if you know what the stationary distribution is, there's no need to actually try to generate a whole bunch of Markov chains to reach that.
there kind of is.
Oh,
let's say it's something
okay.
you can't actually sample from on its own.
Okay.
Right? Let's say it's not some easily characterized distribution where you
Okay.
can think of some, I don't know, simple inverse to the CDF to, do uniform and then apply
Right.
inverse transfer.
That's the inverse method of
Sampling random variables.
Sampling random variables.
Or
Right.
let's say it's some other problem where you have a really complicated function that you're trying to, get a handle on, optimize or somehow, get a stationary distribution within.
Right.
If the state space, or if the space of possible values
Uh-huh.
is large enough and strange enough, it
Uh-huh.
may be actually incredibly difficult to, create a random sample from it.
Uh-huh.
But you could think of a Markov chain, perhaps, that would allow you to sample from it indirectly, as opposed to using some inverse transform or something like that.
Right. So you may know what the stationary distribution is, but to fully characterize it would be very difficult.
Exactly.
Or to
I guess to fully use it or use all the math that would allow you to sample from it or create a tool from it is difficult, but creating a Markov chain to approximate it is not as much.
Right. So, right. Okay.
And there's a couple of fun results. I'm not going to go over them here, but you can actually, any discrete distribution, you can sample from using a Markov chain.
Oh, okay.
Or a series of Markov chains. If it's a discrete distribution, there is a construct of Markov chains you can make, which will simulate that random variable.
Okay. So a Bernoulli distribution, a binomial distribution, a Poisson distribution.
Yeah.
These are all distributions that you can
arbitrarily closely approximate
with a Markov chain.
Yeah.
Oh, okay. Or a series of Markov chains.
Or a series, because some of them end up being a little bit trickier. So, like, if you consider, what is it? Something like a negative binomial.
Okay. Which is another discrete distribution.
Another discrete distribution. If you consider something like a negative binomial, the way you end up approximating that is essentially you have a bunch of linked Markov chains which behave like geometric random variables. Because a negative binomial is a sum of geometric random variables.
Yes, it is. Yes, of course.
So you end up essentially approximating a geometric random variable, and then you make that one part of your matrix. You add a bunch of zeros, and then you have one transition point that it goes to the next geometric random variable.
Okay. Cool. All right. Wow, I've learned a lot, and that's
that's the idea behind, when you hear things like burn in time or when people let it run for a little bit. It's usually because of mechanics like this. Essentially, we know theoretically that if you run it for long enough, you'll get where you want to be. But if you start far enough away, it could take a long time.
Right. I know we're getting into really abstract conversations here, but I think this is still one good topic to finish on, which is how do you let's see if you know what the final stationary distribution is supposed to look like. You can't characterize it fully, so you're going to use Markov chains to approximate it somehow. How do you construct a Markov chain to eventually get there? That's a very abstract question. Can you offer some general abstract guidance?
Well, there's one way you can do it that's kind of I suppose the one way, or there's a couple of ways of doing it. Okay. Usually it is not, usually it's not easy. Like there's no hard and fast rule. There's no way of saying, oh, you just do this.
Okay.
But if you know the probability of going to a state, and I'm thinking about this right now.
Okay.
I know I've proved this before.
Okay.
But I don't know if I remember it exactly right. So I'm kind of going to be thinking through this as I work.
Okay. That's all right.
But we can consider an arbitrary distribution, right? So let's consider an arbitrary discrete distribution, right? Once again, I'll just use the notation F. That's it. We'll consider a distribution F.
Okay.
Right? And let's just say that it's equal to the probability of equaling 1, probability of equaling 2, etc., etc.
Okay.
And we can go up to n if we really want. Actually, we're going to have to go up to n for the case I'm thinking of. If we want to think of a Markov chain, which has a limiting distribution or has this as a non-trivial one eigenvector, because you could just have the case where it's the identity matrix and then this is the one eigenvector. But the non-trivial case, and this is the part where I'm not entirely sure about the exact structure of this, but if we think through it, maybe we can get to it.
Okay.
We want to think of something that arbitrarily approximates this. So this is a finite distribution. It has some probability at each and every state.
Okay. Yeah.
So I'm going to write out.
Yeah, let me see if I can help you out there.
It's probably not easy.
Yeah. Here, use this pen. This black pen is.
I also might not write firm enough.
It's so easy for this marker to erase itself if you don't.
It's really strange.
Yeah. Okay. All right. Go ahead.
And now I'm just trying to remember exactly what it is. Because what we want is when we multiply it by itself, you end up with something that gives you this back.
Oh, okay.
We want this multiplied by this to give you that back. And that's not always easy to do.
Mm-hmm.
And I'm trying to think about it, and I feel like...
You're trying to reverse engineer a matrix multiplication.
Well, it's not really that.
No?
Oftentimes you can think about this process and the way it will behave.
Okay.
And you can get to solutions. Like, I know I usually... I guess this is a great example of how you figure out what Markov chain fits what you want to do, is you sit there and you think about it for a little bit.
Okay. But okay, why don't we step back? Generally speaking, when you're using Markov chains, how do you decide, how do you figure out what Markov chains to use to eventually get to the final distribution that you want? Well, what's your strategy? Is it because you have a lot of experience?
Oftentimes it's motivated by the problem.
So, okay.
Actually, something I was solving here relatively recently. I'll talk about it in very general terms. You might have something where, let's say we're doing something where we're just, I don't know, we're counting or we're stepping up and down.
Okay.
A very general, very common type of transition probability matrix is going to be equal to this kind of thick diagonal matrix. Actually, I should give more than n states to give you a good idea of what's actually going on here. I should give you probably at least 3. This idea of matrix with a thick diagonal is actually very common, or you could call it a block diagonal. So let's say that the probability of staying at 1 is 1 minus p. Probability of going from 1 to 2 is, of course, p. And then everything else is 0, right? And then let's say when we're at 2, there's a probability of going to 1 of, what is it going to be? I want it to be p q. A probability of going from 2 to 3 of p 1 minus q, and a probability of staying at 2 of, that's going to be, I think, just 1 minus p. 1 minus p. If we sum that up, it's going to be 1. It's going to be 1. We're good.
Yeah.
Right?
Yeah.
And then we can consider the same, we can actually just, if we want to, we can just make it very easy for ourselves and make it the same for everything.
So this next entry here would be p times 1 minus q?
Yes, exactly.
Right.
Same pattern over and over again. And then, of course, at n, we're going to have the same sort of thing as we had at 1. So we're going to have 1 minus p to stay at n, and then we'll have p, or we can, to make it perfectly symmetric, I suppose, or to make it perfectly nice, we'll make it n minus 1 to n, or n to n minus 1 is p minus 1, and n to stay at n is p.
Okay. Right.
This is actually a pretty common structure in Markov chains.
Okay.
There's a lot of different cases where you might just be stepping by 1 each time, and you don't know exactly how that's going to work.
Okay.
But in the case I was dealing with, essentially what you were doing was you were sampling one thing, and you were replacing it with something else. And then you were counting afterwards a third or some quality of these items you're sampling.
Right.
So if you're at every point replacing one item from the sample with a new item, at any point, if you're counting up, like let's say it's red balls in a bag, I mean the ball and urns or whatever it is, right?
Yeah.
At every point, the count can only change by, at most, 1. And oftentimes it stays the same.
Okay.
And so this very naturally becomes your transition probability matrix.
Okay.
And you know what these probabilities are, and so you get the Markov chain out of that.
Okay. I don't fully understand what's happening, but then again, I asked a very abstract question, and there's still a lot for me to understand about Markov chains before I could understand that in rigorous detail. So, hey, I appreciate you trying to come up with an example off the top of your head just to satisfy my very abstract question.
Yeah.
No, I've learned a lot already, and you've done a really good job explaining many of the details and the rigor. So thank you very much, Chris. Is there a reference that you could recommend everybody to read to learn more about this?
There's a lot online.
Okay.
If you search up Markov chains, if you search up introduction to stochastic processes, you'll probably get stuff. I think one of the books I used for a course was called Introduction to Probability Models by S. Ross. If you search that up, I'm pretty sure there is legitimately freely available PDF.
Yes, yeah. So the last name of the author is Ross.
Yeah.
Okay. And beyond Markov chains, is there a book about statistics or math that you're reading right now that
No.
No?
I took 4 years of stats, and I'm taking the summer off before I do my master's.
Okay, fair enough.
And besides what I'm doing at work, obviously.
Yeah. Okay. And so we know that you're going to go to ETH Zurich to study skagnostics and copulas. Do you have any publications that we can look forward to?
There is one that may be coming out. I don't really want to jinx it, so
Okay,
I'm not going to say where might be coming out.
Okay.
But it's something essentially where me and a professor we went and we filtered the Hillary Clinton email database that caused so much consternation in the U.S.
Okay.
And worked on displaying the data and creating an interactive tool that anyone could use.
Oh, okay.
It's currently online, actually, at rshiny. I can't even remember the URL of this thing anymore. I'll be able to see that, actually.
And I'll make sure to put the link in the video in the description of the video.
And that links to a working paper we have posted on ResearchGate, as well as all the work we've actually done.
Okay, so it's
still currently a work in progress. Not to say that if you go there it's unfinished. It's actually at this point pretty usable and pretty much what we wanted.
Okay.
But I guess let's just say that WikiLeaks is not very forthright about how they do any of their extraction.
Okay.
And that's led to a whole host of problems we're still trying to address.
Okay.
In terms of the data quality and how clean it is.
Okay.
And a lot of that's just because, like I said, WikiLeaks, despite talking about honesty, integrity, openness, and transparency, is none of those things with how it extracts the emails. And so we have to reverse engineer pretty much all.
But what you're doing is completely legitimate.
Yeah, no, these are not the Podesta emails. These are the publicly released emails, which were released by the State Department in PDF form. The reason why we use WikiLeaks is because the PDF form is very hard to read via machine, and it's very difficult to extract information from. But WikiLeaks has done some stuff to already take those PDFs and put them into HTML form.
I see.
And once they're in HTML form, you can use regular expressions and a bunch of other stuff to extract the information you want from the emails.
Right.
But these are all legitimately, legally released emails.
Right.
Vetted by the State Department. They're all redacted. They all have case codes on them. So
right. Okay.
It's not like illegal emails we're looking at.
Yes, of course.
We were careful about that.
Yes, of course. So this is rshiny.math.uwaterloo.ca/Clinton. And I'll put this link into the description of the video as well. Okay. Thank you very much, Chris, for taking the time to explain all of this to me and everybody else watching this video. This is Christopher Salahub, who just spent the last hour and a half talking about Markov chains. I'm Eric Cai, the Chemical Statistician. You can, of course, visit my blog to learn more about statistics, math, machine learning, and chemistry. Thank you very much for watching this episode of The Central Equilibrium, and I hope that you learned something useful today.